Hi everyone, today I want to talk about one of my papers, the Traffic Light Management System by Federated Deep Reinforcement Learning. Okay, let's start with a very brief introduction. Nowadays, intersections are managed by traffic lights, so inefficient traffic lights may cause numerous problems, such as line delay of traveling and massive waste of energy. Existing traffic lights use fixed preset program without considering the real-time traffic condition at the intersection, which is not efficient. Our goal is to use smart traffic lights. In these lights, the status of traffic light is set based on the real-time data obtained from the current traffic flow at the intersection. One of the methods to reach this goal, which many researchers also propose, is reinforcement learning. In reinforcement learning, there exists an agent that interacts with the environment to learn better action policies to maximize the objective reward function in the long run through trial and errors. In general, the reinforcement learning model is composed of three components. The first one is state space. The state of the agent must contain sufficient information about the environment so that it can lead the agent to learn efficiently to minimize the traffic load of the intersection. We consider a two-dimensional matrix as our state. Each cell will be filled by 1 if a vehicle fills the corresponding grid, otherwise it will remain 0. As you can see, since vehicles may have many different arrangements, so our state space is very large. The second component is action space. Our action is to activate the green signal adaptively for a set of non-intersecting lanes. The simulator that I've designed is composed of two different actions. The green signal is active for vertical lanes and the green signal is active for horizontal lanes. And finally, the reward function. So far, our agent has seen the traffic situation and made a decision. Now we have to evaluate our agent's decision, which is by the reward function. The reward function that I've used is cumulative waiting time difference, which is always a negative number since the vehicle's delays is always positive. And by making better decisions, the agent will get fewer negative rewards. Okay, so far we have defined state space, action space, and reward function. Now we have to connect them somehow. We connect these components through queue function, which is described in here. In order to use this queue function, firstly we have to define a queue table, which is a combination of every action and state pairs. As I mentioned before, as our state is very large, so that it is impractical to search and find every state and action pairs. So instead of directly building a queue table and solving the queue function, we approximate the queue function by a neural network. Specifically, we use convolutional neural network. This is the convolutional neural network that I've designed. The input of our system is our state that goes into two convolutional layer, then put through a fully connected layer, and finally will be mapped into the action space of our system. Okay, so we have designed a deep reinforcement learning model that our agent is training. Usually, other papers stop at this point. I mean, they use deep reinforcement learning agent in the first intersection, they use the same agent in the second intersection, and so on. These agents are doing the same training process individually in different environments. This separate training may cause some problems. Firstly, it may cause low convergence speed because agents are training individually. Secondly, it may cause a biased learning and overfitting to local dataset because agents are training over their particular environment and they have never seen other environments. So in unprecedented traffic conditions, they may show a very poor performance. Our general idea to solve these problems is to connect agents that are working in different intersections. In our method, agents are training their models independently and concurrently in different environments. After each training episode, agents share their model parameters with other agents through the global server. So agents will benefit from each other's training data without actually seeing the data. This concept is known as federated learning. This is a general federated learning training process involving n participants. Agents are training their models over their datasets independently. After each training episode, agents share their model parameters with other agents through the global server and download some parameters from the server. Now let's take a deeper look at the sharing parameter protocol that is happening here. This figure shows a parameter sharing protocol between participant I and the global server. Through the red path, the participant sends its parameter to the server, and through the blue path, the server sends its parameter to the participant. Okay, let's start from here. In the beginning, our participant carries these model parameters. Then our participant trains its model for one episode. These are model parameters after one episode of training. Then participant computes the local gradient vector by subtracting these models. Now we have the local gradient vector that shows how parameters of agent I are changed to become more accurate model during the recent training episode. This information is exactly what other participants need to know in order to avoid overfitting. Okay, we have to send this local gradient to the global server. In our paper, we assume that participants only share a fraction of gradient vector. For example, they share 10% or 20% of the gradient vector instead of sharing the whole vector. Also, they share big values in the gradient vector because they contribute more to changing the network during the recent training episode. Okay, finally, the participants share the gradient vector to the global server. The server gets these gradients from the participant and adds them to its model parameters. Okay, that was all about the red path. Now let's talk about the blue path. The logic behind the blue path is exactly the same as the red path. These are new parameters of the global server. These are the parameters of the global server last time that this specific participant requested the server to download the parameters from the server. Now we compute the global gradient, select a subsection, and send them to the participant I. This participant receives these gradients and adds them to the corresponding local gradients. Okay, that was all about this figure. As you can see, this figure is constructed from two main parts: participant and the global server. Now let's take a look at each one of them algorithm. Here we have the algorithm related to the participants. As you can see, this algorithm is constructed from four main parts. In the first step, the participant has to download the global gradient from the server and add them to local parameters. What is happening in here? In the second step, the participant has to train the neural network. In the third step, the participant has to compute the gradient vector which is here. And in the last step, the participant has to select a fraction and upload the local gradients to the global server. Select a fraction and upload the selected gradients to the global server. Okay, that was all about the algorithm related to the participants. This is the algorithm related to the global server. As you can see, this algorithm is constructed from two main parts. The first part happened when participant uploads the gradient vector. In this situation, the only thing that the server has to do is receive the gradient vector and add them to the global parameters. What is happening here? In the second part happens when the participant wants to download the gradient vector from the server. In this situation, the global server has to take these three steps. In the first step, the server has to compute the global gradient. Then the server has to select a fraction and send the global gradient to the participant. Select a fraction and send the selected gradients to the participants. And in the last step, the server has to update this parameter. This parameter will be used for the next download request from this specific participant, which is this parameter. Okay, that was all about the algorithms. The problem was the agents were training individually that caused to low convergence speed and bias learning. So we connected agents by federated learning, so we expect that our proposed federated deep reinforcement learning model leads to faster convergence, increase in accuracy, and avoid bias learning. To prove our claims, we have designed two experiments. This is my first experiment, which is based on convergence speed. As you can see, the federated learning model converged in 800 episodes, but deep reinforcement learning model converged in 2000 episodes. This happens because different participants are communicating in federated learning approach. This extra information from other agents increases model convergence speed. Okay, and also as you can see, the federated learning model reduces the average waiting time of the vehicles in comparison with other strategies. So from this experiment, we have seen that our proposed federated deep reinforcement learning model increased the convergence speed and also reduces the average waiting time of the vehicles. This is my second experiment, which is based on unprecedented traffic condition. We made an unprecedented traffic condition in our intersection from episodes 333 until 666. As you can see, our federated learning models perform much better than other strategies, which shows that a parameter sharing protocol in federated learning approach avoided bias learning and overfitting to local data sets. So from this experiment, we have seen that our proposed federated learning model avoided bias learning and overfitting. So we have proved all of our claims. And finally, this is the simulator that I've designed. This simulator is being controlled by our proposed federated deep reinforcement learning model. At each time step, the system will activate the green signal for a set of non-intersecting lanes based on the current traffic flow, traffic condition at the intersection. Thank you for your attention. This is the simulator that I've designed and is being controlled by federated deep reinforcement learning model. Thank you. These are my references.